So let us start. Sparse matrix. The sparse matrix basically is a matrix where most of the data are zero. Let us think about a data that we receive from satellite for weather forecast. So the data will be very big, very large chunk of data we'll get, and we are not sure that how many of it will contain the value and how many will contain zeros. But the size will be bigger. So in such kind of conditions where the data available are very less and the size of data is very huge, at that time of situation we use a matrix called a sparse matrix. Basically, how many elements should be zero and what are the percentage of zeros in total elements. To call a matrix a sparse matrix is not fixed. It depends on the programmer or the memory that is available to us. Let us assume that this is sparse matrix. Very few entries are having 10, 15, 60, 90 and all those, and rest of the data are 0. And by the side of the data, the location is mentioned in black. So in this matrix you see there are 14 non-zero elements, but this matrix is 9 cross. This matrix is a 6 cross 9 matrix and only 14 non-zero values are there. It means 54 locations are there, and if we take this matrix as a set of integers take 2 bytes. So to have this matrix we need 54 into 2, that is 108 bytes. But if we want to save only the values, that is only 14 non-zero values, so 14 into 2, that is 28 bytes will be sufficient for us to store the data. So look at the difference, where is 108 bytes and where is 28 bytes. So for efficient storage and processing, we use a sparse matrix. So is there any alternative way of representation is needed? Yes, obviously, if we want to save the sparse matrix, we need an alternative method of representing it. So each element of the matrix is uniquely characterized by its row and its column position. So we take a triplets, that is I, J and value, that is easily represents the non-zero values in the matrix. And in the sparse representation of matrix, there are 3 columns we will take. The first will indicate the row, the second will indicate the column, and the third will indicate the non-zero value. If this is the matrix that we are taking, then for this we can take the first element in the sparse matrix. 6 indicate number of rows in the matrix, 9 indicates the number of column in the matrix, and 10 indicates that there are 10 non-zero element in this particular matrix. And after that we'll write the rows and columns where the non-zero elements are present. Here you can see at 0, 0 location value 10 is present. At 0, 7 location value 20 is there. Similarly in 5th row second column value 90 is located. So like that this big matrix will be represented in this small way. So the number of rows in the sparse matrix will be number of non-zero elements or non-zero values in the sparse matrix plus 1. Here you can see if there are 10 non-zero elements are there in the sparse matrix, we have taken 11 rows. Why? Because the first row itself will indicate how many rows are there, how many columns are there, and how many non-zero values are there in the matrix. So the size of this alternative representation will be 3, that is number of column in the number of non-zero elements in the matrix plus 1. So this is the size that we need to represent in the alternative method of presenting a sparse matrix. In the original sparse matrix, if its size is 6 cross 9, then we need 108 bytes. But in this case, 11 into 3 and 2 bytes for each memory location, it will take 66 bytes. So look at the difference, that if the matrix size become larger and larger, the difference will become more and more. So this kind of representation will help me in saving memory. So for representing a sparse matrix, let's say we are taking a class here, class sparse matrix, and we are defining a constant that is maximum size of 20, and we are defining a matrix that is maximum size and 3, and we are having two operations, that is transpose and addition operation. So let us try to understand the algorithms for transpose and addition of matrix operations. As we already know how the transpose is being done, it means column value will be transferred as row value, or row value will be transferred as column value. Here if we are transferring the column values, then this is how the value will be transferred, and this algorithm will be applied for all the columns. Now for this matrix, let us take, for this matrix let us try to do the transpose. We'll define a area where we'll save the transpose, and the size is supposed to be the same as the original matrix. So the first column will be shifted to the second column. Second column will be shifted to the first column in the transpose matrix, and third column will remain the same. It means A I1 will be shifted to B I2, A I2 values will be shifted to B I1, and A I3 will remain as B I3. This is our transpose matrix. Now here again you can see we want to save our value in the form of triplets I, J and value. But in our transpose matrix we will be writing in the form of J, I and value. Let us discuss the algorithm for transpose of matrix. Here these two matrices we are taking, we are trying to understand the algorithm with this given data. So here we are taking a variable called sparse matrix. It means we are saving the transposed sparse matrix in ST, and we are defining variable row, column, I, J, K and val. Row indicates row number, column indicates column number, and val indicates how many non-zero entry are there in the sparse matrix. So in the original matrix, 0, 0 location indicates the row, we will save it in row. 0, 1th location of original matrix will save it in column, and 0, 2th location of the original matrix, it indicates how many non-zero values are there, it will save in val. And if val is not equal to 0, it means this matrix contains some data, then only transpose we can do. If the whole matrix is a 0 matrix, then what is the use of doing any transpose? Whatever we saved in column, we want to transfer it to the first entry of the transpose matrix. The second entry, that is row, will be transferred to the second entry, and the value will remain the third element in the transpose matrix. 6, 9 and 10 will become 9, 6 and 10. Let us go to details of the algorithm. So here with this algorithm, you can check here on the row of the initial matrix, all the data are sorted. Similarly, on the transpose matrix also, the first column is in a sorted order. So that is what we are going to do here. We will take I equal to 0, we will take J equal to 0 to number of columns, and we are taking one more variable K. K is 1 and K is less than equal to value K plus plus. If the value in K1 location equal to J, initially let us say J equal to 0, it means 1, 1 location of the original matrix, if it contains 0, then we want to shift the data. That is first location to the transpose matrix 0th location, original matrix 0th location, we want to save it in transpose matrix first location. The third column of original matrix which will be written in the third column of the transposed matrix. So this work we are going to do repeatedly as long as this if condition is satisfying. This if condition will help me to write all the data in a sorted order. Hope you understood this algorithm. If you have not understood the algorithm, kindly take some value and try to work out with this algorithm. You will be able to understand it. Let us try to learn about addition of matrix. Now let us say this is a matrix A is given. We want to add to the sparse matrix B, and this is what we are getting. Now in order to understand this, I am going to explain you using algorithm. So here the size of matrix supposed to be same. In the sparse matrix B also 6, 9 will be there, and in the resultant matrix sparse matrix 6, 9 will be there. Maybe the number of non-zero element may vary, but the size of the matrix supposed to be the same. So the number of rows and number of columns supposed to be same. It means so A00 value I want to write it in C00 and A01 value I want to write it in C01. Now while adding in the same row and same column, the location of the value in the first matrix and the location of the value in the second matrix are same, then this particular algorithm will be using. It means if AI0 and BJ0 are same, and if AI1 and BJ1 are same, then what I want to do, I will be shifting the data but after addition. That is AI2 plus BJ2 I will add and I will save it in CK2 location, and then I will increment I value by 1, J value by 1 and K value by 1. Similarly, if the addition I am doing and the value are there in the same row but in different location, in different column of the same row, it means what? If AI0 is equal to BJ0 and AI1 is greater than BJ1, then what I have to do? B values whatever are there, I have to shift it to C, because they are not in the same location, so I cannot add. So that's why, so what I do, I take the B matrix and write it in the C matrix. Similarly, if AI1 location is less than BJ1 location, it means these two values are again different in the column, but they are present in the same row. Then I have to transform the data AI data to CI data. If the elements are present in the different row itself, it means here AI0 is greater than BJ0, then entries in the B I will be shifting to entries in the C to the resultant matrix, and J and K value I will increment by 1. Similarly, one more thing is there, while adding still some more rows are repeated left out in matrix A. Then directly I will copy matrix A and write it in matrix A. So the same thing may happen with matrix B. If some left out elements are there with matrix B, I will transform all the value whatever are left out to matrix C. So this is how I am going to do matrix addition. And at last, how many entries are there in the row? I will write it in the C02 location. That will indicate me the non-zero elements in this particular matrix.